Hello everyone. Today let's solve the problem number 33. Search in rotated sorted array. So you can just go through the question. You can just understand the question through the examples as well. They have given the examples here as well, right? So you can just understand the question via examples as well. So I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given an sorted array nums. You can clearly see here we are given an sorted array nums that might be rotated at some pivot index. So that might be rotated at some pivot index they have given here. You can clearly see the array is 4 times rotated here. We have 0, 1, 2, 4, 5, 6, 7, right? So this is sorted, they have clearly mentioned, and this is 4 times rotated here, right? So that might be rotated at some pivot index, and the task is to find the index of the target number in the array. So we have been given target as well here, integer, this one target. So we have to find the index of the target in this array. So here they have given 0, and 0 is present at the 4th index. That's what the output that we have got here. You can clearly see 1, 2, 3, 4, 0, 1, 2, 3, 4, right? This is the 4th index. So we have to display that index of the number, right? So if the target does not exist, we have to return -1. We have to keep in mind this one. If the target does not exist in the array, so we have to return -1. The rotation here means a part of the array is shifted to the end while keeping the overall sorted order intact. So I have already said this one, overall sorted array, sorted order intact. So what we need to achieve here, we need to achieve this one in big of log n runtime. They have clearly mentioned here, we must write an algorithm with big of log n runtime complexity. So let's see the approach first. I hope the question is completely clear. You can clearly see here, like I hope the first example is clear. In second example, they have given target 3. Target 3 here, this is not present in the array, so we are displaying -1. Same goes with third example as well. Target 0 they have given, only one element is found, that is 1. 0 is not present in the array, output is -1 here. I hope the question is clear. What we need to find, we have to find the index of the target number that is present in the nums array, right? So let's discuss the approach first, and then discuss the edge cases, all the edge cases one by one, and then write the code, and let's discuss the complexity of the code that we have written. Initially, let's go with the approach. So let's understand the this one. Let's understand the approach step by step. First thing we need to keep in mind is we are going with the binary search approach. Just keep this one in mind. So first, what we need to understand here, we need to understand the array structure. So rotated array has 2 segments here. One is sorted and increasing. Other is also sorted but shifted to wrap around the array's end, right? So here first let's go with, sorry, what happened here? It's fine. We are going with the binary search, right? So let me give here, let's go with the binary search. And first step is we have to understand the array structure here. So a rotated array has 2 segments, as I have said. One is sorted and increasing, other is also sorted but shifted to wrap around the arrays end. So first one, let me give here, understand array structure. Second thing, let's come to the main logic here, using the binary search, or let me give here, utilize binary search. Let's see how can we utilize binary search here. So first thing, let's make use of the binary search because it allows us to achieve the big of log n time. They have clearly mentioned in the question as well. We have to write the algorithm in O of log n time, big of log n time, right? So what we are doing here is, let's compare the middle element with the rightmost element. Let's compare the mid element with the rightmost element, right? Let's compare the mid element with the rightmost element to determine which part of the array is sorted. Why we are doing this one? To determine which part of array is sorted. Array is sorted, right? So this is one thing. And the final thing is we have to adjust the search boundaries. While I say we have to adjust the search boundaries, I'm speaking of left and right pointers, right? Left depending on the segment where the target could this one exist. So we have to, in simple terms, we have to adjust search boundaries. This one, left and right pointers, right? Depending on segment where target could exist. Depending on the segment where target could exist, right? So this is pure binary search, if you know the binary search correctly, right? So let's finally come to the third step, nothing but the termination. Let's see, while I say termination, we have to continue until the left and right pointers converge or meet. So continue until left and right pointers meet or converge, right? So if the target exists, left pointer will point to its index. If the target, whatever the target that we need, if the target number exists in the array, then left pointer will point to the index, point to its index, right? Otherwise, we are returning -1. So if the target is not found in the array, we will be returning -1. So this is the approach that we will go with. First thing is, we have to understand that we are going with the binary search approach. So what is first thing? Let's we have to understand the array structure, right? A rotated array has two segments, we know. One is sorted and increasing, and other is also sorted, but it is shifted to wrap around the array's end. Second thing is we are making use of the binary search. We are making use of the binary search. What we are doing here, we are using binary search because we have to achieve the solution in big of login time. In the binary search, what we are doing, we are comparing the mid element with the rightmost element to determine which part of the array is sorted, first thing. And second thing is we are adjusting the search boundaries left and right depending on the segment where the target could exist, right? This is simple, pure binary search. And the third one is termination. Termination, when I say termination, we are continuing the process until the left and right pointers meet or converge. If the target exists, then the left pointer will point to its index. If the target is not found, then we are returning -1. So this will be the approach that we will be going with. Let's discuss the edge case one by one and then write the code. Let's go with the first edge case, nothing but target is at the pivot point. So let's see here. Let me consider the input here. Nums 670, some random numbers here. 1, 2, 4 and 5. Target 0. So target 0, because we are going with the edge case, target is at the pivot point, right? So the output here will be 2. This is found at the index 2, right? 0, 1, 2. So the output will be 2 here. So this is for the target is at pivot point, right? Next, let's go with the second edge case. Nothing but target does not exist in the array. So while I say target does not exist in the array, so we are going with the input 4, 5, 6, 7, 8, 9, 10, anything. Just give here. Let's consider the target 26. So the number 26 is not present in the array. So we'll be giving output -1. If the target is not found in the array, we have to display -1, right? So the output here will be -1. This is for the condition target does not exist in the array. This is the second edge case. So let's move on with the third edge case. So let me come here. Third one is single element array where the target is absent, right? So single element array means, let me consider here one. Let me consider, sorry, nums one. One element in the array. Then target, let's search for 0 here. So the output will be obviously -1. So we have only one element and we are searching for the element 0 which is not present in the array. So the output will be obviously -1. This is for the condition single element array where target is absent. Right? I hope this is clear. Let's move on with the next edge case, fourth edge case, right? So this is for the single element array where the target is present. We have only one element and also that will be the target here in this case, right? Let's consider the same thing, and this time let's consider the target as 1 here. So the output will be 0, right? This is present at the 0th index. Only we have one element and the target is the same thing, same element. So the output will be here 0 because it is present at the 0 index. This is for single element array where target is present. So this is for the fourth edge case. Let's move on with the final edge case or the fifth edge case. Nothing but no rotation in the array. While we have no rotation in the array we can consider like this, right? 1, 2, 3, 4, 5. And let's consider the target. Let me give here target 3. Here the output will be 2, right? So this 3 is present in the second index. You can clearly see here this one. So the output will be quite obviously 2 here. Sorry, the output, I mean, it is present at the index 2. It starts from 0, right? This is fine. This is for the condition no rotation in the array. So these are the edge cases that we need to keep in mind. So first edge cases, we went with target is at the pivot point, right? You can clearly see here. And second edge case was for target does not exist in the array. And the third edge case was for single element array where target is absent. And the fourth edge case was for single element array where target is present. And the final edge case is for, sorry, final edge case is for no rotation in the array. So I hope all the edge cases are clear. Now let's start writing the code. I'll explain the code while writing the code itself, right? So as we had discussed in the approach, let's go with the binary search. Initial step is let's initialize the search bound as usual. We are going with the left and right, right? So I'll just give here left equals 0, right, left points to the first index and right points to the last index. Nothing but the nums dot line -1 here. Let's perform the binary search. Initially, left less than right, then we'll proceed further. So we have to find the middle index first, right? So to find the mid index, I'll just give here left plus right by 2, or we can just make use of the right shift operator here. This is also fine. So the condition is if the left part is sorted, then the right part is rotated. Then we have to search in the right part, right? Suppose, let's go with the simple if condition. If nums of mid, as we had discussed, this one, mid element is greater than the rightmost element. How we can write? We have considered right. Nothing but nums of mid greater than nums of right here. Sorry, what did I do here? Yeah. This is fine. If the middle element is greater than the last element or the rightmost element, then left part is said to be sorted and right part is said to be rotated, right? So let's write the same thing here. If target greater than nums of mid, then what we will do, or target less than or equal to nums of right here. So then what we will do, we will search in the right part. Then if what if the target is less than nums of mid, then we will search in the left part. So this is the condition that we have already discussed in the approach, right? So here first let's search in the right part according to the condition here. I'll give left equals mid plus 1, else let's search in the left part, nothing but right equals mid. This is fine. Else here, this is for the condition left left part is sorted and right part is rotated, this one, right? Else left part is, I mean right part is sorted and the left part is rotated. For that, how can we write here? I'll just come here. In this case, let me come here. Let me give else here. So this is for the right part is sorted, right? The same thing. Let me copy the same thing here and make the necessary changes, man. So here, target greater than nums of mid, this remains same, and the target less than or equals to nums of right, this one remains same thing. And what we will do, we will search in the right part first. So left equals mid plus 1, same thing. Else we will search in the this one left part, nothing but right equals mid. Finally, we have to check if the target exists at the final index or not. How can we write that? I'll just make a simple use of the ternary operator. So nums of left, if it is equal to target, then we are displaying left, else will give -1 as per the question, right? So let me format this one once and we hit the run button. So just give me a second here. Why this is saying unknown network error? So yeah, let me hit the run button again. So what happened here? Line number 1, target I have misspelled. Just give me a second here. Let me hit the run button again. Wrong answer we are getting. Let's check what we have done wrong here. So what mistake I have done here is in line number 14, we have to give and here, right? We are considering this one as well along with the target greater than nums of mid. I think I copied this one, line number 8, and I forgot to change this one. Same thing I have kept here. So let me run the code again. So now we can clearly see the sample test cases are getting passed here, right? So let me hit the submit button now. So you can clearly see all the test cases are getting passed. So the code works absolutely correct. So quickly, let's discuss the time complexity and the space complexity. So the approach that we went with here is binary search on the rotated array, right? Or you can just, in simple terms, you can just say binary search. So the overall time complexity here would be big O of logarithmic n or big O of log n. By binary search reduces the search space by half n each iteration. We know this one, right? So the time complexity here would be big O of log n. So what will be the space complexity here? Then the overall space complexity would be big O of 1 because they are not making use of any extra memory here, right? Everything is done in place. We are just making use of the pointers here. You can clearly see. So the overall space complexity would be here big O of 1. I hope this is completely clear. So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.